BBC Basic for the AGON Light for beginners. Some basics. Hi everybody, my name's Tel and this is Tel's Bench, and today we'll be running a small course in this video to run over the main elements of the BBC Basic as it relates to the AGON Light, which is a relatively new single board, super fast 8-bit computer. So BASIC, which stands for Beginner's All-Purpose Symbolic Instruction Code, originally invented in the 1960s. In the early 1980s, Acorn Computers in Cambridge won a contract to design a microcomputer for use in schools so that all children would have an equal opportunity to learn about computers and programming. This was called the BBC Micro and needed a programming language, so a version of BASIC was chosen for this and created BBC Basic. This was ported and rewritten for the AGON Light along with altered and new functionality. There is a lot to cover, so we will not be fully covering the assembler part of it, as this requires a specific skill set and will be done in a different module at a later date. Games and other programs written for the Acorn BBC Micro in assembler will not work on the AGON Light, and this is because the AGON Light uses an EZ80 processor and the Acorn BBC Micro was fitted with a 6502 processor, which would not be compatible. So we're in the basics section now. These are just some of the fundamentals that you will need in order to create any code in BBC Basic. We've already loaded and run Basic and you can see the prompt there. The first thing I'm going to do is to enter some basic code, but in Basic you will always use a line number as a prefix for each line that you write. So we'll put in 10. And in uppercase you put the keyword, in this case print, and I'll say hello 10. And I'm going to put line 20, print, hello 20. So we've got a program. Maybe I want to change the line numbers. Maybe I've had to put some line numbers in the middle, like on 15, so let's go and do that. So at line 15 I'm going to put print hello, 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 hello. Okay, I've got that now. So if I CLS, clear the screen and then list, I've got that. But that's kind of not what I want to do, because I want all my lines to have a 20 gap between them. So if I need to put more lines in, I can do that, as you just saw. So I now want to renumber that so it's all back to normal. So if I put in renumber, and then I can say I want to go from 10 onwards to 20. And now if I list, look at that, I've got 10, 30 and 50. But let's go back and change it back, because I feel a bit extravagant today. So 10 onwards, and then we'll actually put it back to 10. Let's see if it's done that. And that has, it's put it back. So I've said from 10 onwards. I didn't specify 10 to 50. I just said from 10 onwards. You can put anything from 1 to 65,535 in for a line number. That is your range. You can't put in 0 because it won't accept it. In fact, if we put in 0, print 0, it prints it, but when we list it, it's not there. It just ignores it. So it will ignore number 0 and just treat it as if you typed it in at the prompt without a number. If you put in 70,000, 70, 123, which is above our range, and I say print 70, it will say it's too big. Actually, I'll teach you another new command. It's a little bit early, but if I want to clear everything I've done, all I have to do is type in new. And now if I list, I've got nothing there. There you go. That's how to enter lines in. The other thing that I haven't told you is if I put in hello, what do you think will happen? It tells me it's a mistake because it needs all keywords to be in uppercase. No lowercase keywords. Those are reserved. Those keywords like print and new and CLS and any other keyword that you can think of. And you can put things like CLS in your program, so you could put it at the beginning. So we've got nothing in there at the moment. A common thing to want to do is to say 10 CLS, and then you can go 20 print some text. Now if I run the program, it says some text because it's cleared the screen first, and I'll run it again and it'll do it again. So that's a useful thing to do, to know how to clear the screen, to know what to do in terms of the case for putting in a keyword, and how to renumber things. So that's quite a lot of information in that small demonstration that I've just done. So we got some stuff in there. So what if I want to change 20 to read some good text? Well, there's something called a line editor, which I can type in. And because that's a star, that means it's an MOS command. And MOS stands for Machine Operating System. So this is a command, one of many commands that you can use to do things on the system. You're going to invoke an MOS command. I don't think it needs to be in uppercase because that's not basic. So it's edit line 20. And now we're actually in the line editor for that. So you can use your cursor keys and so forth and back delete to change things. So I can cursor to there and then I can just enter that. And now when I run it, which has to be in uppercase, some good text. So far, in just a few minutes, you've learnt the ranges for the line numbers. You learnt how to use the print command. You've learnt how to renumber them. And you've learnt what happens if you go outside the range. Okay. You've learnt what a keyword is. The fact that it has to be uppercase. You've learnt how to write a very basic program using the print command and the CLS command for clearing the screen. You've learnt the line editor facility, edit a line using the cursor keys, and how to enter corrections. So that's some of the basics that I wanted to give you. Enter will always enter a value, and escape will leave it unchanged. So if I just go back into that again and I say start edit 20, and I do my backspace there to delete those, or back delete, and I put in really bad text, and instead of hitting enter I just escape. Okay, it says escape and it hasn't changed it. So that's the basics done. So this small section, this basic section, is just to really get you off the starting blocks, and you'll be seeing many more of these keywords as we go through the material. Okay, so this is the order of operations section. Order of operations is basically if you do a number of actions on one statement in BASIC, it's the order in which it evaluates those expressions. This in itself is a big subject because it covers quite a lot of things, and I'm going to try and make it as simplified as possible for you so that you don't get overwhelmed with it. So in the order of operations, the first thing I want to look at is something called PEMDAS. Does anyone remember PEMDAS? I'm sure if you come from America you definitely do. If you were educated in the UK you might have been taught BODMAS possibly, or if you're a newer student these days maybe PEMDAS, who knows. Both of them mean the same thing, and they are an acronym which refers to the order of operations in a mathematical sense. So if we've got a handful of numbers, 3 plus 2 divided by 7 multiplied by power of 2, etc., etc., this will help you work out how, if you wrote them out, it would be calculated. And in fact, all computers, if they're worth their salt, will actually evaluate them in that order, because that is the correct mathematical way to do it. So we'll use the American acronym because I think it's better, it resonates with me better, and there's actually a little rhyme which helps you to remember it, and it's please excuse my dear Aunt Sally. I have no idea what Aunt Sally did, but it's been useful. That is the little rhyme, jingle, whatever you want to call it, will help you cement that in your head if you don't know it. If you do know it, that's fine. But for those who don't, it's an important concept in the overall scheme of order operations for the AGON Light BBC Basic, because it's a major part of it. There are other things that go into this mix, but we'll cope with those later. I just want to fixate on this one first to get that out of the way, and then we can move on. And the reason that we want to do this is because it will help you understand what you can actually write in and how it will be interpreted by the computer. But it's good to understand it anyway as a basic concept, and then the other things will fit in around that. PEMDAS stands for the order in which they're evaluated from top to bottom there, or if you wrote that out from left to right, it would be from left to right. So parenthesis, anything in parenthesis will be the first thing to be calculated. So in your line of calculation, from left to right, if you've got a parenthesis, you have to go and calculate what's in that first. Then you apply exponents. So wherever those exponents, powers or roots that you find, you'll apply that to that item, calculation inside a bracket or parenthesis, if you want to use that word, and you apply those from left to right where you find them. Multiplication and division a pair, like a dynamic duo, as are addition and subtraction. So multiplication and division, you go from the left hand side of the expression to the right, and you'll say, if I find a multiplication or a division along the left hand side to the right hand side, as I find them, I will do that calculation. And then you do the same thing with addition and subtraction. So there's kind of 4 operations done in 2 stages, with all of these different things in. So what I did was I prepared a PEMDAS questions to illustrate how this works. So if I do chain, you haven't seen that command yet. That means basically run something that you load, which is a basic file. So chain, I can write it out chain, or I can write it out with a ch dot. So it's going to be PEMDAS questions. And that gives you 3 examples. Please excuse my dear Aunt Sally with the PEMDAS acronym before it. So let's have a look at the first one here. So we don't have any parentheses here. So that's the first thing we look for. We don't have any powers there, or exponents, I should say. But what we do have is a multiplication and a division there. So those things that we need to do. Right, so if we go left to right, we leave that because that's an addition. There, leave that at the moment. We'll apply this rule and calculate this because it's a multiplication. So that's 35 times 2, and that's 70. And then we've also got division, which is in the first dynamic duo there. I will say 70 divided by 10 equals, yes, 7. Yes, right. And then we'll go back to the beginning and run through again. So we've got 10 plus 7 equals 17. So what I'll do for the next 2 is I'll actually let you think about it. I won't tell you what the answer is, and I'll give you a few moments and you can think what the answer is. So here we've got 10 minus 5, so we're not going to be doing that. 35 times 2, so that's 70 divided by 10, and you know that's 7. So what's the answer going to be there? It's going to be 12, isn't it? Because we've got this 70 divided by 10, and then we go back to the beginning. We go 10 minus 5, which is 5, plus 7 equals 12. And then the last one, we've actually got an exponent and a parenthesis in there. So a parenthesis first, so 3 times 2, which is 6. Raise it to the power of 2, which is 36. And then we go back to the beginning, and we say multiplication. 5 times 36 is 180. Divided by 10 equals 18. So that's what I think it is. So if I load up the PEMDAS, I said that with an English accent. Now let me load the answers. So you see, remember this one, it was 70 divided by 10 plus 10. That is the way we do it. We don't just start at the beginning of the line and go through it. We use this rule to find out what we need to evaluate first. So I hope you found this PEMDAS little refresher useful and interesting. But now we're going to go on and look at the other operators that need to be included in the order of operations. It won't take too long, and we can then get on with other things. Okay, so in the last bit we did PEMDAS, and over here I've got a legend, and I've also got order and expressions, which covers the stuff we did in PEMDAS. So we covered the parenthesis, which is this one here. We covered the exponent. We covered times and divide, and we covered plus and minus and how they work together. So what I'm going to do now is I'm going to talk about some of the other ones. So I'm going to talk about the mod and div. Those are the two that I'm going to look at now. What I did was I wrote a small program to give us some examples. I'll list that now so you can see what you're going to see. So we're going to be doing multiply, divide, which is multiplication, divide, mod and div, and how they relate to each other in terms of priority, what gets evaluated first. So we've got 7 examples here, and for each one of those we print out this, which is just telling you what we're doing, which is the sum, or the expression if you like. And then we actually print out the answer because I type this in again there. And then we tell you what priority what is over what. And that's done 7 times. So I'm just going to run this. I will go through them one at a time. So we know that the multiplication and divider have got a higher priority than the mod and the div, and the mod has got a higher priority over the div. So let's have a look at the examples we did. So here in example 1 we've got 5 times 6, div, and then mod. Well, do you know what a div is? Let me tell you. A div is a divider which gives you the amount of times a quotient or an integer on either side of it goes into the left hand side. If it was just 6 divided by 4, this would be 1, because there would be one time that you could divide 4 into it. The mod is kind of the opposite, because it gives you the remainder. So 4 into 6 would go 1, and you'd have 2 left over. So let's look at these sums then. So for 1, we know this beats that. So this is going to be 30, 5 times 6. So it's 30 div 4, which means we can divide 4 into the left hand side 7 times. And it means that is prioritized over this. And then we do the same for mod, go with the same divider, and we find we get a 2, because that's the difference between 28, which is those two divided by 4, and then the remainder is 2. And so that also applies there, but it's a mod this time, not a div. And in this one, which is 3, again, these are prioritized over the div. So we have 10 divided by 2, which is 5, divided by 2, which means that can go in there twice. 2 2s are 4. Okay, and again, divide over div. And this one is the mod. 5 goes into 10 twice, so that's going to be 2. And if I divide 2 into 2 with a mod, I'm going to have no remainder. So again, that's the priority. For the 5th one, we've got a mod and a div. And if we look at our legend over here, mod beats div. So we know we do this one first. So 20 mod 11, 9 remaining. We divide that by 3, and that can go in there 3 times. So that works, and it means mod over div. On this one, 6, we've got div gets evaluated first. That's got a higher priority than plus and the minus. Div is executed first, so div 5, div 3 means that they're going once. So that's 1. 10 plus 1 is 11. Priority div or mod over the plus sign. And this one, number 7, is the same thing. So in number 7, again, div takes priority. So we'll go 5 div 3, and that's going to be 1, because it'll only go into 5 once. And then we take 1 away from 20, so that gives us 19. And again, it's priority div over subtract. For the other ones in here, so you've got functions, variables. These two, they are indirection operators, and this is just a binary add or subtract, and you've got a not. Those are the ones that we haven't covered, and also the 3 and or, EOR, exclusive or, and or, which are binary and logical operators. So those and, EOR, and or sound like a donkey. EOR. What I suggest that you do, if you're interested, is to actually go and experiment with these and look at the literature. I've got this line here. It says, for the few remaining, suggest you experiment and refer to the manual linked in the comments section. So there is a document written by about 5 people really over time as it's evolved into the AGON Light version of BBC Basic. It's crammed with stuff. It's far too much. It wouldn't be far too much to include all that stuff in this video because it would be so long you'd fall asleep or become bored with it. I'm just taking the main parts that are useful, but we'll run through the whole thing and I'll go into some of them in a bit more detail, and some of them I'll just tell you to go and either look it up or look at it if it's of interest to you, because for example, when we come to look at the trigonometry section, things like sine, cosine and so forth, but really there's no point in going and doing that stuff because for some people they'll have forgotten all about that and they won't even remember what a sine or a cosine is. This is not about teaching anybody to learn those mathematical practices, but it's just about telling you where they are and what they do. Okay, those kinds of things I probably won't be covering in this video. So that's the kind of approach I'm taking to it. If there's a particular requirement comes out, oh yeah, please do this, then I'll do that in a separate video. But I thought covering the order operations PEMDAS was an important thing to cover and to get out of the way first of all. So with that out of the okay, so let's touch on variables, then we'll have a look at the assign and compare operations. So with variables, the naming for variables has got to start with a letter. So we can have letters and we can have numbers in the variable name. If you take a look here, we have real numbers. Okay, so that is just an example. It could be A, it could be B, C, whatever. And they're stored in 5 bytes for real numbers. I put there mathematically not real because, as far as I know, a real number should be infinite potentially. Right, so this is not truly real. Some maths genius is probably going to call me out and tell me I'm wrong, but I believe I'm basically right, although I might not have phrased it correctly. So integers, they have a suffix of a percent mark there, and they're stored in 4 bytes. So these are whole numbers and they're also static. So there is no Boolean assignment. You can't assign a variable to be Boolean, but you can test the value that variable has. So for testing Booleans, if it's 0, it's going to be false. If it's -1, it's true. But if it's minus anything, it can be true actually. So that's where we are with that. We come on to strings. So strings are suffixed with a $. Strings are allocated up to 255 bytes. So that's done dynamically. If you type in $, equals, in quotes, 1, 2, 3, 4, 5, you'll get 5 bytes. If you allocate it at 255 bytes, you'll get 255 bytes. So if you allocate $, for example, to be, in quotes, something that's 50 bytes long, and then you decide, oh, actually I want to make $, equal something that's 100 bytes long. What happens is it will allocate that 100 bytes somewhere in memory and then point $, to that, and where $, originally pointed to will no longer be referenced, so it doesn't automatically release that memory. So if this thing may happen and you don't want it to happen, then you should do one of two things. You should either allocate the maximum so you can change it, or find some other way of managing memory and maybe using dereferences. So for assign and compare operations, I thought I'd just put a few things in there about that. Talk about it a little bit. These dots are not decimal points, they're just bullet points. So just ignore the dots, really. You'll probably know this if you've done any programming anyway. So if you have and you understand this, to just skip to the next section. But for those who might be coming in fresh, if you like, the equal sign can be either, this is one thing I don't like about BASIC actually, the equal sign is used either as an assignment or an equality. And what that means is if I test a value, so I conditionally want to do something, like with an if statement, if A equals B, that means I'm testing the equality, and based on whether it's a true or false, then I can do something or do something else. And these really speak for themselves. So if you're doing a test, these are all tests. So saying if the left hand side is greater or equal to the right hand side of this operator, then act appropriately, and it just goes down there, not equal, less than, or greater than. That's it really. I just wanted to touch on those because it's part of it and because we need to just understand how these things work. So on the assign and compare ops, what I did was I wrote a little program, a little noddy program, so I'll just list it for you to see what it does. So it really goes down these assignment equality operators here. The first one it covers really is just that. It just says for one assignment, this is an assignment. And it does a similar thing for equality and all the other ones. So let's just run that and see what it shows up. Oh yeah, and then what it does is it actually, after printing that, it then goes and does the calculation. It's if 3 equals 3, then print equal, etc. So you'll see if I just run it now. So we already did assignment and we did equality. So if 3 equals 3, then print equal. Otherwise, print unequal. And it was equal, obviously. 3 is greater than or equal to 2. Then print greater or equal. And that's what it did. If it's less, then it's smaller or equal. If it's not equal, print not equal. And it was not equal. If it was smaller than, then it's going to be smaller. And we say it's 2 is smaller than 3. And is larger, 3 is larger than 2. So that's it really, it's quite simple. And once you start using these operators, you'll find they come second nature, they're just common sense to you. I'd like to just recap what you've learnt, what you've seen. We did an overview of the history and where we are now with AGON Light and BBC from its beginnings. And basic as a basic concept, where that came from, or when that came from rather. And we did some fundamental things like line numbers, you did print commands, various other little commands that you learned, renumbering and numbers, the line number range, if you remember back to that, what keywords are and how they have to be uppercase. We did a little basic program, a couple of them I think actually, and a line edit, how we could edit a line using the start edit and then the line number. We did the order of operations, the basic flow of priority for various operators, in particular PEMDAS, which is please excuse my dear Aunt Sally. We spoke about that. And then we did some other order of operations, some other symbols, how they work. Loops and code flow. Right, so we're here today to talk about loops. And those loops are the repeat loop and the for loop, and also program flow. So let's just stick with the for loop and the repeat loop. The concept is very, very simple. So with the for loop, the times that you would use this kind of loop is when you know the number of iterations that you want the loop to do. It's saying for a variable, and we'll just call that x, is equal to 1, to an upper limit. So that will go from 1 to some other number which is higher, or perhaps less actually. So you could go from 10 to 1. You could step backwards. So let's just concentrate on the forward one first. So x equals 1 to 5, and it will go one increment at a time of 1 every time it cycles through the loop. In the middle you have the OR code, and this point at the end you're saying, okay, if I need to go and do this again, otherwise I'll just carry on with the code that's below this next x. So you write your code in there, all the things that you want to do while it's in this loop, and it's as simple as that. So when would you use this over anything else? Well, let's have a look at the anything else. So the other one is the repeat until. That allows you an undetermined number of iterations, with the exception of there is a condition, and the condition here is whatever you want it to be. So you could artificially create this loop really using a repeat. So here you say x equals 1, okay, and then we could say your code there, and then after this, but before the end, we could say x equals x plus 1, and then in the condition we could say while x is less or equal than whatever the number was, which would be 5 if we're trying to repeat this. So the difference between the two really is one is a set number of repetitions, and this one is an undetermined number of repetitions, other than that there is a condition that it will repeat under. So we don't know necessarily what that is. It depends on what's going on inside, but it will eventually get to a condition that you've set there of being true. If it's true, that's the point it will exit the loop, and that is the fundamental difference between the two. So where would you use this, or when would you use this? When would you use it? You'd use it, for example, if you wanted to print out a table of results. So you've got a number of columns, and those columns could be, I don't know, let's say we're doing exam results. It could be your ID, then the student name, the subject, and the score which they got in their exam. So you need to go in an X direction and a Y direction, and in that case what you would do is nest two loops. So you'd have a for loop inside a for loop. So typically you would say the outer loop would be for Y, so we start off with Y, and then we across for each row, and then you go in and you go down one, and then you do it all again. So that's a kind of example. But what would happen if you wanted to jump out of the loop early? So something else might have happened which would want you to intervene and stop the process and the iterations that would normally occur. What would happen then? Well, yes, you could. You could exit. What you could do is to artificially set X when an arbitrary condition occurred in the loop, and then make it exit the loop. But the point I would make is, why would you want to do that when you could use repeat? If you know it's a fixed number, then use the for loop. If you have an indeterminate amount of loops, use that one and just put a condition in. It's far easier and far cleaner to do it that way. Where would you use a repeat loop? Well, it could be a number of things, honestly. I can't think of a specific example off the top of my head, but I'll think one up in a minute, and we'll do some examples. And then the last one I wanted to talk to you about was the if then else. So if then else, and it doesn't have to be if then else, it can just be if then do something, right? So here we got if the condition is such, if it's true, then you do an action, and you have an option to do else, do something different. So this in these square brackets means that this is optional. So with the if statement, some of the limitations about that really are compared to other languages. This is all on one line. Everything you do with an if statement is on one line, and that means that you're limited to the number of space you've got in a single line. So let's go and do some examples then. If you're enjoying the video so far, like and subscribe if you're not already a subscriber, and let's get on with the show. So let's have a look at the for loop and 2 or 3 different ways that we can actually manipulate that. So let's put some code in then. X equals 1, x equals 1, 2, 5, step 1. That is optional actually. That's step 1, unless you want to put something different in, but I'll just put it in there anyway. And let's just print X, something very simple, and then go next. So that will just print the values of X as it increments. If we run it, that's what we get. Fairly straightforward, right? So let's use our edit command, as you learnt in the episode 1, assuming you watched that, edit 10. And let's do something different. Let's go backwards. Let's start at 5 and go to 1 and say -1. What will happen now? Yep, it goes backwards. Something else you can do. So let's have a list again. What else could we do with that? It's not 100% necessary, but there are some occasions where you will need to put it in to stop you getting into a problem. Edit 30, just to keep it tidy. So what do we want to do now? What if we want to print them across the screen? So I'm going to go back and I'm going to change 10 again. I'm going to make it smaller. I'm going to go from 1 to 3. So with edit 20, I'm just going to put a semicolon there. That means it will print on the same line and go across the page rather than going down. That didn't work very well. So what did I do wrong then? Yes, so I went from 1 to... okay. Edit 10. Forgot to change this. To change that as well. So as you can see, this hasn't been rehearsed. This is straight off the peg. So actually, let's put a CLS on line 5 and then renumber it. Bit of revision here from episode 1. Right, so we've got starting from 10 CLS, and then we go from 1 to 5, and then we print X, and it should go across. So let's try it. Yeah, that's what happens. It goes across the screen till it hasn't got any more room. The reason it prints it there is because of the print formatting. So the first one starts over there somewhere, and then you've got another one, and you haven't got room for the fifth one. There is a way to change the width of those columns if you're using smaller numbers. And I might be able to do that now actually. I'll see if I can do it from memory. Okay, so at percent, which is the print formatting, at percent equals 0.20004. And now if I run it, you can see them all on the same line. So it's something we haven't touched, the print formatting, and I will get to it, but basically you can set the precision, you can alter the width as well of the frame if you like. Okay, so we made them smaller, but we will be touching on that later on, either today or in another episode. Let's have a go and look at repeat. So I'm going to go new. You remember that from episode 1, it gets rid of what you've got, but there is something I haven't told you about. You can actually type in old. Now, if you haven't actually typed anything in, you can bring back your old program. But what I will do is I'll do new again, right, and then I'll go 10 print. Oof. Now if I type in old, what happens? I don't get it. So it's a once only chance. So try and remember, if you do something with a new command and you weren't quite ready, don't go putting any commands in, otherwise you'll lose it. So I'll go now, new again. Now again, new again. CLS. Right, okay. So let's do our repeat. We'll try and do the same thing as we did in the for loop, but we'll use the repeat loop structure. So repeat 20. I think we're missing something actually, but we'll do a percent equals a percent plus 1, 30 until a percent is equal to 5. 115, I'll actually put in percent and I'll do a renumber. So let's have a look at what that looks like. Okay, repeat loop until a percent equals 5, print a percent, and then a percent is incremented by 1. So if I run that now, oh, there's something I haven't done. What was it, I wonder? Well, let's try putting in a percent as a value first. There you go. Now notice the difference between this one and the last one. First of all, the for implicitly in its structure, it initializes this variable to a number. We didn't do that. We just assumed it was going to be a value, which would be 0. And also, the way that it's structured is it will print a, but it didn't print 0, did it? Right? So on 5, if I now, on line 5, if I do a percent, it's equal to 1. And then list, and then renumber, list again. So we've initialized a percent to a value of 1. And now I run it. I still only get 1 to 4. Right. Well, that's because at this point it drops out. So what you need to do here is come back and make that greater than 5. So we must include 5. Now if we run it, we'll get the 1, 2, 3, 4, 5. And in the same manner that we did a reverse, we could change this so that on 10, I'll just put it in, I'll just type in a percent equals 5, and then on 50 we put in is smaller than 1, and then we ought to adjust 40. So edit 40, getting lots of use of the edit line command. You know, once you start using it, you won't have any problem. So let's run it. So that's both of those loops going in forward direction and going in reverse direction. So let's have a look at the if statement. We're just going to do it on one line because if statements can only be on one line. So I'll put one line in, 10. So if I'll put a equals 2. Something else you haven't seen yet, I'm adding another statement on the same line using a colon. And b percent equals 3. And then in my if statement, which will be on 20, I type in if A% equals B%, well then I'll do just that. Run that now. It's not doing anything. Well, why is that? If you look at the line, it said if they're equal, which they're not because we set them to different numbers, then it would print equal, but we didn't give it a else statement. So what we'll do is we'll go back and we'll make them equal first. And we'll make that equal 3. Now I can run that and it will say equal because it knows they're equal. Well, let's make them unequal again. Give it a different number this time. And then we'll edit 20. Else print unequal. And it says unequal because now they're back to being unequal. I've got 5 for A% and B% is equal to 3. So we've covered the structure and the use of the for loop, the repeat, and the if condition, which is the for loop, why you would use a for loop, the repeat, and why you would use the repeat, how you can go up and how you can go down, because you can count negatively or positively. And you could also do that with decimal points as well, so you could count up in increments of 0.1, 0.2, whatever you wanted it to be, you can make those changes. Because I want to talk about some of the issues that you might get when you're using these loops that could catch you out. Okay, so we've got something called a go sub. So a go sub is a subroutine. So 20 go sub 100, which we haven't yet got. So 30 I'm going to go next. 40 to go end at the moment. On 100 I'm going to say A% equals 1 plus A%, and then 110. I'm going to do return. So what should happen, it should jump to this subroutine here and it will say A% equals 1 plus A%, so it'll increment it in a simple way. In line 25, which I haven't done yet, I'll say print A%. So let me renumber. So currently we have go sub 100 because that's where it is. What happens when I renumber? Now I list and the go sub call has changed to 60. So the renumbering is intelligent enough to realise that it has a go sub somewhere that this is pointing to, and it then changes it after it's done the renumbering or during the renumbering process. So let's see what happens when we run that. Okay, so the reason that it started from 6 and went to 10 is because it still had the value of 6 from the last time we ran something. Even though we got rid of the program, it's a static variable and it stays there. So somehow you need to clear that in order to, get rid of the problem. It's something to be aware of, and that's why I wanted to show it to you. So I could run this again now. What do you think would happen if I ran this again? Would it start from 1? Or would it start from the upper number? Well, remember I said it doesn't clear it. So if I run it again, what happens? There you go. It goes from 11. So the lesson is, if you're going to use static variables, A%, whatever, then you must clear those down before your program starts. So you must set those to initial values, or just don't use them. So I think what we need to do now is to change the A% to just an A. Okay, so that will work fine and we won't have this problem. Right, so we set it at 1 originally, and so we can run it and we'll find it goes from 2 to 6. So I've re-engineered the loop a little bit, and we got 5 on line 5, A equals 0, and then 10 we go sub 100, and 100 is where the for loop is. Okay, but it's also, that for loop is also inside the go sub. But what's going to happen is we're going to jump out on line 120 when I gets to 7 to 140, and 140 is the return. If it ever came back from that to line 20, that would terminate at this point here with the end statement. That means end, stop the program. Okay, but we're going to 100, so we've gone to do I from 0 to 150. Print I, and if I equals 7, which is where we want to jump out illegally, then we'll go to 140. There's no go to there, it's just implicit when we say then 140, and that is to just go to return. So it started there, but because we didn't pop it off, we've got a problem. So that's because the last thing on the stack was the address for a for loop, not a go sub. If I run it, no go sub at line 140. Yeah, it's got yourself all confused. So that's why you need to avoid doing these kind of things like jumping out of a loop. Don't ever exit out of a loop unless you plan to come back into the loop. In that case, you can do it. And the same thing for a repeat. Yeah, same thing for any of them actually. For a go sub and repeat. On a function, when you get to those, it will be a return statement that you have to exit. On a function, the return statement looks like an equal and then a value. And if it's a procedure, it'll be an end proc that you'd expect to hit. So you'll properly come out. Procedures and functions. So in this episode, we're going to concentrate purely on functions and procedures and what they do. Hello everybody, welcome to episode 3, BBC Basic for the AGON Light. So in this episode we're going to concentrate purely on functions and procedures and what they do. So on the right hand side you can see a nice little diagram there. It shows you, first of all, in line 10 we're assigning to the variable a 30. And then we do some things down here. And we see what the expected result was and what the actual result was. And I'll explain to you how this works. So let's deal with procedure first, because a procedure is the first thing that comes up in the program. We define the procedure up here and we end proc there at 130. So that's where the procedure starts. That's the definition, keyword there, which means we're about to define the procedure. All procedures are prefixed with the word proc and then the procedure name itself. And then your code goes in there and then the word end proc. That signals to BBC Basic that the procedure is terminated now and it can go back to the next line. So in this particular example, example 1, all we're doing is calling the procedure and then it goes back. So then we print A. Line 50, we call a function called testfunct, and it's one there on line 150, and we do something in there, and when we see the equal sign, it has the same effect as the proc here. It's the end of the function, and we're basically, or it may not be the end of the function, but it's the point in the function where we end it. So because we're starting with an equal sign, it says the same thing, we're done now. Because it's a function, we're sending back a value. So that goes back there, and then it prints it. And then we print A again. And then that's the end. It's stopped. These two colons here, really, they are only there to give us some visual space so we can see what's happening in this code. When we're at line 30, so we printed A, we expect to get 30, and we did get 30. And then we call the proc and see what happens. So let's go into the proc, the procedure. With procedures, we can either pass no variables at all, or we can pass in numbers into the procedure when we call it, but we have to define variable names to receive those numbers. And then we hit in here this thing which says line 110, and it says local A. So what local A means, we're declaring a local A variable, but it just happens to have the same name as the one on line 10. And what it does is it pushes this A onto the stack, and then it's free to use in the procedure without worrying about doing anything to its shadow name up there. So we're assigning 22 to it, and then we print it, we're printing it within the proc, and we expect 22. That's what we're expecting, and then we end the proc. So we go back there and then print our A there, and we see what we're expecting. There we're expecting 30 because that shouldn't have been corrupted in any way by this process, unless we wanted it to. But in this case we don't want it. But we're printing at this point at line 120, and then we call our test function. So it's fn test func. So that will return a number back, and again we're not giving it any parameters. Okay, so we're getting no parameters into there, and it's the same thing applies. Local A, do what you want with A then, and then you can send this local A value back, and it's popping that off the stack, so this goes back to what it should be. Now, you don't have to use existing variables, but I'm doing this to show you the effect that it actually has and how it works. So I've got a program here. If I list it, I'll just show you it. So all the things that you see on the right hand side we've done there, but we're printing on 20 there, print A, but I'm actually telling you which line it's printing on. So I can see whether what I expect here is what's actually happening on the program. So if we just follow that through, we get to the test proc here, and then we go local A, and it's pretty much as you see it on the right hand side there. All right. So what I'll do is I'll clear that. Well, I don't even have to clear it. I could just run it, and let's see what happens. So it's showing us on line 20, our actual is 30. Right. So we expected that. On line 120 down there, we set A to 22, and we expected 22 to come out when we printed it. That's exactly what happened. So we go back to line 30, and then we print our good old A there, and expect it to not have been corrupted. And in fact, that's exactly what happened. We got 30. On 50, we call the print test func, and it goes there down to here. Again, we protect our external A. We assign it 39. It goes back, and we expect 39. And what happens? We get 39. And then we do the same thing for 60, except we're printing our good old A there, and that's what happens. Okay, so that's that. Right, you can see I've changed now to example 2. So in example 2, we're actually calling a procedure here. So we're putting that value A in here, and when we come to this called procedure here, so that goes to there. All we're doing, we're not doing a local now, all we're doing is assigning to A 66. Now what it does here, well, it proves it in what you're going to see, but I think we're not explicitly using the local, but it automatically, when you assign that A to this, it will give a replica value of it, if you like. So we can do something to it, and it's not going to affect it, hopefully, and then we print A and expect to get what we set it to. But it won't affect the original A. And the same thing for this in this procedure. So it's been called there, and it returns the value 66. And what we find is, let's see what we find. So I'm going to CLS this, and now I've just loaded episode 3, example 2. We're now passing our A to both the proc, test proc, and we're also passing it to the test func. You will also notice that we've lost the local word from there and lost the local word from there. And what's happening is, if we call the test proc with A, we'll come along there, and what happens is, if it's the same name as this external one, it's the effect basically of making a snapshot of that and storing the other one on the stack. So we're not actually going to affect this, and we can assign a value to this and it won't corrupt this. That's the idea. So then we print our A, which is effectively our local A, explicitly set it, and we will get 66. And when we come back to the next line, which is there, we'll expect to get the good old 30. And then we'll call the function. So we're calling the function with A, and we expect to get 66 printed out when we come back, returned from A. So we go into the function there, and we'll assign A 66, which is what we were given, and we return it. But again, it pops it off. So we go back to the original A, we hope. So on line 60, print A should print 30. So we'll get this one, this one, this one, this one, and this one. So the order will look wrong like the other one did, because on the second print we're actually getting it printed at line 120, but then it'll go 40, 50, and 60. I'll list the code for you there. You can see that these have changed here. We've got the A being sent to the proc, and we've got A being sent to the new function here. And that was 39, but I changed it to be 66 like the other one. Yes, I'll let you run your eyes over that for just a few moments so you can compare this side to this side. But essentially, other than giving the function a parameter here and here, and changing one value over there, and taking out the local, the word local, we're accomplishing the same thing. Now, the reason I'm making these distinctions here and showing you explicitly what happens when you pass parameters that shadow in really something outside is it's an important thing to understand, that you see what the relationship is between that which is passed to it and what you can do to it on the inside. Of course, you don't have to use something that's shadowed on the outside. It could be something completely different. They could be parameters that you don't find anywhere else, which aren't in another procedure, so they're in the general code. So that might not matter because you might not be using it, but it's valuable to be able to see that. So let me run this now, and let's see if we get what we expect. So on line 20, we expected 30 because that's what it was originally set to. Oh, well, that's what we got. So we jump to line 100, and then we take out A and we assign 66 to it. The original A is now on the stack. We're using the sort of local A even though we haven't said it's local. Then we print A, we expect 66, and we got 66. Then we come back from the proc and print our good old original A, and there it is. And we do the same thing for the function. We get to the function, we give it A, but we're expecting a function, test function there to return a value for this print statement, which it does. It again assigns A to 66 and sends that back. So we get 66 here, and it's printed it here. And then lastly, we just examine our global A, if you like, over there, and expect it to be uncorrupted, and that's what we've got. So this is what I wanted to show you. It might seem over the top to be talking about this over two examples, but I think it's important for you to understand, because I know that there's been confusion for some people by questions I've seen online about why we're using this local. Well, what happens to the variables we pass? Are they affected? So this is proof of how it operates. I haven't seen this explicitly written except for using the word local. In terms of what happens when you shadow another A, if you like, in this case, outside, I haven't seen anybody explicitly write that anywhere. So I thought I'd do some experiments, and it appears to support what I'm saying. Okay, so let's talk a little bit in general about functions and procedures and kind of summarize what we've learned today. Both functions and procedures can be called with a friendly and meaningful name. So you saw the names that we used today. It allows you to write a little code pocket, if you like, once. So you're not writing the same thing over and over again. So it avoids code smell and repetition of code. You only want to write code once, hopefully. Execution can vary depending on the parameters passed. So you can have the same code running, but what you put in will give you a different result, either by function or by execution in a procedure. And again, we refer to the code base, keeping it tidy. And also you can protect, as you've seen, shadowed variable names. I mean, that term I'm using, it's not something that's written anywhere. So for a procedure specifically, it doesn't return a value, as you've seen. You can only execute. So it provides parameters to allow different results. The program could ask you, what's your name, what's your age, where do you live, what languages do you talk, and it could give you a response on the screen based on that. So some examples could be, you print in report, create a splash screen, or you modify data. A function always returns a value. A value return can vary depending on the parameters. So the examples there, you convert centigrade to Fahrenheit, calculate an equation, work out body mass given body parameters. So, you might have a little program that you want to use to find out what your body mass is and put in your waist measurement every day, for example, and your weight, and give it your height and that, and it might store it for a while. And then you might use a procedure to plot your graph and show you how your body mass is doing. Is it going up? Is it going down? Is it within acceptable limits? So there's some possible uses for it. I'm sure you guys will think of 1,000 different ways of using procedures and functions, but these are just ones I came up with quickly. And actually, there isn't really a whole lot more to say on those. I think the idea should be that you will try those out when you start to write code and see how useful you can find it. Print formatting and reading CSV files. Okay, so welcome to the channel. My name's Tel, and today we're going to be looking at episode 4 of the BBC Basic for Beginners on AGON Light, and we're going to be dealing with all things around print. First of all, what we'll do is just do the basics, which you've already seen a little bit of anyway, but we're going to look at what follows the print keyword and how that can be used. So on the right hand side there's a bit of a legend there, and it says 1 there in the top left hand corner. That's because this is only the first part of this video, because after we've done some of the basics, then we're going to move on to comma separated files and reading from those, and then formatting those results into a table, and then extracting some statistics out of the data. Very fundamental statistics, I have to say, but nevertheless this is really a mechanism to get you into the groove, as it were, in terms of producing some sort of report from data you found elsewhere. So that being said, let's get going. So straight to the keyboard now. The print list is all the things that follow the keyword print. So we have a string, that you already know, an integer, which is a whole number, and a real number. So what we'll do is quickly run through those three, so I won't waste your time, we'll just get straight to it. 1 day. Print 1 day. There we go. Now if I print an integer like 4, that's strange, isn't it? It appears a little bit to the right. Why do you think that is? Well, that's because the fields are set up to 10 characters wide. So this is a 40 character wide display on this one, so we could only get 4 of these in. So if I count from there, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If I was to print another one, it would appear 10 characters over. But you notice when we print text, it goes to the left. So text is always justified left and values are always justified right. And a real number, if we do that, we'll print that in, and that will be 4 point something. It again will print on that boundary, but it's coming towards the left because we've got so many decimal point parts of that number. That really deals with the 3 main things you can print: a string and a value, whether it be an integer or a real number. So let's take a look at something else. Now, I talked about print separators. So the print separators we've got are a comma, a semicolon, and an apostrophe. So let's do some examples of that. So if I print a string first, so I'll put hello, my number, and then I put in a value. So this will appear directly after the string because it's a semicolon. And then I can add more. I can add, spell that right, and it says hello, my number 1 friend. So that's how you can combine those things. We can also have multiple statements like this. So if we put some numbers in, we could put in a 1, 2, 3, and 4 actually. And you'll see 40 characters wide, and there they are. So what happens if I do the same thing with print strings? If I do 1, 2, 3, if I go comma 4, 5, 6, then same thing, right? It uses those 10 width fields, which are adjustable by the way, and it floats that to the left hand side. So we've also got something called an apostrophe that we could use. So if I typed in 1, 2, 3, 4, 5 apostrophe 6, 7, 8, 9, 0, what do you think would happen there? Okay, apostrophes will actually put them on different lines. It will split them. So that's the effect of that. So we've also got other ways of positioning the text. We've got something that isn't listed on the right hand side, the tab keyword. So I can put tab, and I can put one value. I can just put the X value, which is always the one that comes first, and then I can put something straight after that tab, and it increments 8 characters from the left to there and starts it there. I could also put tab, and now I can actually give it a second parameter, and so I can say 8, and maybe I want to go down to 15, line 15. So this is the X position and this is the line position. And now type I'm in the middle. Well, not quite in the middle, but you get the point. So there's a few things about strings that you didn't know. Well, alright then, so this is the final bit on the formatting. So A%, which is a static variable which you've seen before, is used by the formatter to format values which are being printed to the screen or a printer if you had one. Bit 0 contains the default width, so field or column, whatever you like to call it. And you saw me printing values with 1, 2, 3, 4, and they spanned the whole width of the screen because it was a 40 character wide screen, and so that's matching with the 10, which is the default, which here you'll see that is hexadecimal 0A. The number of digits displayed, pretty straightforward, right? So how many digits do you display decimal points? B2, byte 2, is the kind of formatting we apply. So 0, which is the general formatting, will apply depending on the size of the number. Exponent will give you, for certain sizes, it will give you an exponential value. So if the number is big enough, it will show you a number like this one to the e to the -2. So the decimal point will flip back to get the value. And then finally you've got fixed, which is going to be my usual go-to format. Now here we've got the string command here. It's not string, that's str$. That takes a parenthesis, that keyword, and you can put a value in it and it will print it. Now if this byte here is set to 0, it will just use a general format. If it's set to 1, it will use all of the formatting information here. So we're not going to do much about that. I'll show you a little demo of it in the next screen, but we don't really need to worry about it too much today. That tells you pretty much what these do. Now if I have a look at the code behind this output, like I've done in my other videos, I show you what I'm doing. So I print what I'm trying to do. So here we've got B1, B2, which is exponential, and then it's telling me these are the bytes there, these are the values that I'm going to set, and then it sets those values, and then we print some numbers. I'm showing what I'm going to print, and then I print it, and then we'll run it and make sure it's doing what we expect it to and explain it a little bit. So this saves me typing stuff in. So in our general format, if the value is smaller than 0.01, then it's always going to be an exponential. So if it's bigger than that, then we'll see the numbers print the way they should be. If it's massive, then you'll get an exponential automatically. In other words, scientific notation. But the B1, which is the number of digits displayed, will have an effect. So if you see on this one, for example, This only allows 3 digits, but it's actually rounding that off. It's rounding it off anyway to 1.2. And then we've got 14 is just 14 because that's so small it rounds it off. So the exponential format we've got. So here we have 111.11 and that prints out as 1.11. So the decimal point is shifted 2 places to the right. And the fixed format, which we alluded to, has got a 02 in there. So in this one, this automatically, even though it's fixed format, it automatically under a certain number will still go to, E minus whatever. And this one is a big number, and then we'll see 1.00 and e to the 10. So that's flipping the decimal point way over, all the way over there. So that's rounding it to a 1, and then it's saying, well, we've got to go all the way across here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Fairly straightforward, but it does take a bit of a while to get your head around what's going on. So I'm not going to spend a lot of time on it. I just wanted to show you that so you at least understand the basics of what's going on there. And then there's one more that I want to show you. So it's the demonstration. So load str format.txt. I'll list that. You can see it's a different program altogether, but it's the same thing. I'm telling you what I'm going to do, then I'm doing it. Right. So in the top one here, we're not using the formatter. All right. So bear in mind this will be general format because we're not using the formatter. So it's just going to give us 1, 2, 3, 4, 5 because we're not using that. If we use it, however, we got 1, 2, 3, 4, 5 as before, but we'll only get 1, 2 because it's picking up this bit instead of using the general format. So this, I think personally, and I don't mean any disrespect to the way it's been written up in the manual, but I don't find it particularly easy to visualize in a single sitting, if you like. So all the information is there, but you have to dig it out. So that's why I wanted to do some sort of visual representation in the video for you, so you had some chance of getting it straight away. I've done it. You can refer to the manual if you really need to do anything special, but for the purposes of this video, we're only going to be using fixed format or integer, and that will be sufficient to do what we needed to do. But I did want to demonstrate it and show you it so you know where it is. You've got it in the back of your mind if you ever need it. So yep, let's go on to the next bit. Okay, so this is the last, probably the most interesting bit of this video for most of you, is going to be some code where we're going to take a file that's got CSV entries in it for, let's say it's an exam. Here's an image of the comma separated values file with some interesting and humorous names. So it'll be a student number, the student name, and the student score. Very simple, very straightforward. Those lines will have a carriage return line feed at the end, so we need to process those to get rid of the line feed. So what I'm going to do now is go through some of the code. Or not some of it, all of it. So I've loaded the program, but I wanted to actually just go through the code so you see what's happening. So first of all, we to clear the screen, then we give this variable the file name. Then it's going to be p4 scores.csv, and then we go and count the lines. So we want to know how many lines we got in this file, and you'll see why later that gets used. In fact, on the next line. So now we know how many lines we've got. We can dimension a dollar array, a text array, basically, to have that number of entries. And then we go and populate the results. So let's find that. I'm on line 50, remember that. So we go down to here. This little bit of code cycles through the data file, and for each line, it removes any line feeds and then adds them to our dollar, which is our array. And then we go back and we need to print the header. So very straightforward. And then we want to count the total score. So I've put this in as a real number. There's our percent at percent, and that tells us that we've got a fixed. We're fixed, but we haven't put any specific number of digits in there. We then go and go through table. We're iterating through it. We're printing the fields in the right place, and we're also adding to the total score. And when we get to this point, we've said, okay, right, at this point, what we want to do is we want to print the total line. And so here is now the formatter. So this is where this all comes in useful. We've got 2 for the fixed format and 2 digits. You know, this is likely to show up with decimal points in it because we're dividing one thing into another in the total to see what the average is per student. And then we go past that and they say, what is the average score? It's the total score divided by the number of students. So we've already looked at the proc pop results, but what we didn't do is the parsing. So this is where it gets slightly trickier, because we're having to use the comma. We haven't had this is not all done for us, we have to go and do it. So we know there's 2 commas, and for those 2 commas we then basically find their positions and use that to then chop those bits out and assign them to field 0, field 1 and field 2. And then finally we get this little if statement there, so it's saying if it's index 0, that's field 0, return that. If it's 1, return that. But if it's 2, then we evaluate that because that's a number in a string. We're going to send that back. So then that's all there is to that code. And now we're going to run it for you. And there we go. Simple as that. Wasn't difficult, was it? So with a little bit of code there, using some procedures and functions, all the things that we've already learned in previous episodes and more, we've been able to go to a file, open it up, read it, process it, and format it into a table. And that was the game, that was the goal of this video, to be able to do that. Logical bitwise operators. So today we're going to take a look at logic operators in a BBC Basic for the AGON Light. And they're exactly the same as they would be if it was on the original BBC microcomputer. So I'm going to start off by showing you a pictorial representation of logic gates, because I think it's far easier for you to understand what's going on when you see this. So we've got several operators here. We've got the AND operator, the OR, the exclusive OR, which is XOR, the NAND, which is really just an AND with a not on the end of it, which is one of these. So that, when connected together, becomes one of these, an AND. But let's come back to that in a minute. So we've got an output facility here to show us whether this is high or low. If it's not illuminated in its color, then it's a low. If it's illuminated, then it becomes high. So we can connect up these 2 inputs, which can be set to on and off, which means off means low, on means high, to these gates, and I'll show you what happens. So this represents the AND, this gate represents the AND operator, AND, that you'll find in BBC Basic and OR and XOR. Although in BBC Basic it's written EOR for exclusive OR, not XOR. There isn't a NAND in BBC Basic, but I'm just showing it to you anyway, because you can create a NAND effectively by using a NOT, and you'll see this, it will all make sense soon. Let's go and take a look at the AND, which is the most simplest one, and it will make sense as to why they're called what they're called. Right, so it's got 2 inputs, so I'm going to give it 2 inputs there, and I'm going to connect the output of that to this, and we can see what happens when we try and change these. So at the moment they're both low, and we've got low as an output. If I connect that as to be a on or high, still doesn't do anything. And if I connect that, now I do get an output. And this why this is called an AND. If this and this are true, then this will be true. That will be a high. Okay, so then we go to the OR. Can you guess what we'd be doing on the inputs with those? Yeah, you got it right. So either one of these being high will create a high there. So let's go and adjust our inputs. Right, you can see instantly we've got a high. That's true. So if I turn that one off, I've still got it. If I turn that one off, I haven't got any output. So it's either of these will give a high on the output. So it's this or that will produce a high on the output. Okay, so let me get rid of that. And then we'll move these down to the next one. Let's have a look at that. This looks a bit different, doesn't it? It looks like that, and it's got no R on it, but it's got an X. What does that mean? Well, I'll show you. So what this actually means is you can have one or the other, right? But it's exclusive, so it has to be exclusively one of these inputs high will create a high on the output. If both are low or both are high, there will be no output. So currently we don't have an output. I'll turn that one on. That's fine. If I turn that one on, it goes off. If I just have this one on, which is exclusive, it's just one input, then it's on. And that's all there is to it. That's an exclusive OR. Although in BBC Basic it's written EOR for exclusive OR, not XOR. Now, finally, we've got this gate here, which isn't represented by a single keyword in BBC Basic, but we can create this scenario in our operators and how we put them together. So let me just manipulate my inputs and put them there, and then we connect this one together. Right. So with an AND, it's the exact opposite to an AND. That's why it's got an N on the front. It says not AND. Right. We could create this actually, and I'll show you how we can do that shortly, but we'll do this one first. So with a NAND gate, if A and B are both high, then the output will be low, which is the exact opposite to an AND. So that's where the not comes in. So got an output there. I've still got an output. I haven't got an output there anymore because they're both high. So if they're both high, it will be a 0, low. If I take these and get rid of these, I connect them in there, and I connect this one here. So they're both high at the moment. What do you think will happen if I turn one of these off? That's right, it will go on. So only when they're both high, it will be low. Any other state, it will going to be the opposite. So that's what I wanted to show you. I wanted to show you first and foremost what a logic gate looks like, which you'd see in electronics. So you can see the physical manifestation of a logic gate. And then that will make sense when we go to look at the operators in BBC Basic. Right, okay, so I decided to do this next bit in Excel. And the reason that I did that, I think it's useful to see a good, big, bright, clear representation of what we're talking about before you even touch the console itself. So we spoke about gates, AND gates, OR gates, XOR gates, NAND gates, yeah. But before I go and do some sums on the console in front of you, I wanted to lay out what this looks like for an integer. So 4 bytes is going to be 32 bits long, 0 to 31. Here we've got all those laid out across the top. We've got a row there called left and a row there called right. And this is on, as if we were actually typing this into the console, see what the answer was. So if you did a print and then a tilde and then a value, a decimal value, it would print out in hexadecimal. The left, I'll type it in here for you. So print tilde, and then the left value, whatever that left value might be, and the right value. Okay, and then you see the result down here. So the way that this works is in the results box for each one of these, there's a formula in there, which hopefully you'll be able to see, yeah. And it's sensing this cell here and finding out what this operator is. Is it an AND? Is it an OR? Or is it an exclusive OR? and then it does the sum. It does the sum for bit 0 left and bit 0 right, and puts the result in the result row for bit 0. And then this is copied all the way across here. So at the moment, we've got an AND in there, and we've got a 1 in there, but there's nothing in there. But if I pop a 1 in there, you'll see this now turns over and gives me a 1. And if I put an exclusive OR in there, it's giving me a 0, because these can't exclusive OR, only one has to be a 1. If they're both 1s, you'll get nothing. If they're both 0s, you get nothing. So remember that, and then we get 0. If it's an AND, we get a 1 in there, nothing in the result, I get 1 in there, and we get a result. And the same for an OR, so if I just put in an OR there, we got an OR there. So we got a 1 at the moment, or we did have before I changed that. So if I change that to 0, we still got a 1. If I change that, I get a 0 again. So I thought this was a useful vehicle to actually demonstrate it. So when we talk about true and false in expression in BBC Basic, you're talking about 0 for a false, and we're talking about anything other than that for a true. So if you type in print true on AGON Light, it will give you -1. Type in print false, it will give you 0. If you're using true and false statements, those are the values it will give it, but anything other than a 0 is effectively true. One of the things that we can do is some manipulation of bits. So if, for example, you had something in memory or from an I/O port on the EZ80 processor, you were looking to see what was coming in, so you set your direction inwards so that you can read the bits on that port, and you only actually want to look at the first 4 bits. So let's set this up on here now. So if we had a, let's do 1, 1, 1, 1, and then 1, 1. Now we're only interested in, on the left, these 4 bits. We don't want to have anything from there. If we then choose to do an AND here, and we AND it with a 1, a 1, a 1, and a 1, we have a result of 1, which is not quite right. Yeah, okay, so I fixed that problem. I didn't have a fixed cell reference for this, so when I dragged it across, I actually got the wrong cell reference. It's okay now. So you'll see we've got 0, 0, 0, 0 there, and 0, 1, 1, 1 for the rightmost 4 bits. We've masked this out. We've got rid of this. We're not interested in it. So that's one way operators can be of use. Very useful actually in lots of different situations. If we make this an XOR, then you'll see the pattern changes at the bottom in the result because it's exclusive. If we start popping 1s in the left hand side of that byte, you'll see they start turning 0 at the bottom. So we've done that. We've done the AND, we've done the OR, we've done the XOR. So hopefully this will have explained it as an extension of what we saw with the gates. But I still want to go onto the console and do a few bitwise sums so that you can have some confidence that what you've actually already seen just now is what we're going to get on the console. Welcome to the Fab AGON emulator console. So as promised, I'm going to actually do some calculations on the console to support what you've actually seen in those tools that I just showed you earlier. I've written a script. This is what I do almost always with any video that I do when I'm showing this kind of thing. It's to actually write a program out. I'll show you the program so you're under no illusions of what's going on, and then I'll run it and we'll see the results. So let's have a little listing, shall we? Okay, so I've got paging turned on so that we can see the top bit and then the next bit. So for each one of those operators, AND or an EOR or XOR, whichever way you want to refer to it, it's EOR in the BBC Basic for AGON Light, XOR and everything else. Right, so we've got basically a truth table for each one of these 3. So all the possible combinations 0, 0, 0, 1, 1, 0 and 1, 1. So you'll see this is printing out what we're going to do, and then it does the calculation. So we expect to see what we expect to see for an AND gate. And the same thing for an OR, it's exactly the same, and the same thing for the XOR. So if I press a little bit further down, and the last bit is the bitwise bit, Same thing, same format. But in this case, we're not just dealing with zeros and ones, we're dealing with actual bit patterns. And then we output exactly what we said we were going to do. Alright, so there you'll see a 33 and an OF. That's done in hexadecimal notation there. And we do exactly the same thing in the output. So let's run it. Well, actually, let me just turn off the paging and I'll run the program. So for the AND operator, we can see it obeys the AND truth table, exactly what it should be. You only get a 1 out when both inputs are 1. I've done this for simple 1 and zeros, rather than doing it for complicated bits, because it becomes more complicated to look at, to understand. So that's when that spreadsheet would come in handy. So for the OR operator, I've done exactly the same thing, and we only get 0 when neither of the inputs are 1. For the exclusive OR, or EOR, we've got 0 and 0 is a 0. Any one of those as a 1 will give you 1 output. For both of them, it's going to be a 0. So that's exactly what you've seen. Now let's go on to the next bit. And for the bitwise use, we've got an OF ANDed with a 33. So that's two 4-bit nibbles, if you like, of 1 byte, if we treat it as a byte for the purpose of this. So we've got 33 there and OF there. So we're only going to see an 03 out, and that's because this 0 will cancel out anything on the left-hand side of that byte, the left-hand 4 bits of that byte. And on here, we've got a F0 and a 1. For an OR, so it will add that 1 in. For the EOR, we've got FF and 01. So you get then an FE because we've only got the 1 there, so you get all the bits on that side, but you'll be missing the rightmost bit on this side. So that gives us exactly what we expected. I could go through sort of hundreds of these cases, but you'd probably get weary of it in the end, and I think you need to go and do some experimentation using what I've shown you if you're interested. It's been a fun video to make, actually. It's surprising how difficult it is sometimes to get concepts across when you're dealing with sort of reasonably complex things. It sounds simple, and it is simple once you understand it and you know it in your head, but because I don't know who's listening to this video and watching this video, it's difficult to gauge how to actually put it across. So hopefully I've put it through at the right level, that the people already know this are saying, oh yeah, well, I didn't know I could do that, or yeah, I knew that. And the people that haven't used it before think, oh, that's interesting, I haven't heard of that before, now I know how to do that, I know how I'm going to go and use that now. Memory map and variables. Well, hello everybody and welcome to Tel's Bench. My name is Tel, and today we'll be taking a good look at the memory map for the AGON Light in terms of the BBC Basic and variables, and how all that hangs together, and the high mem, low mem, top and page variables which are inspectable, what they mean, and how you can determine how much space you've got left for your program. We're also going to see how those variables are stored in memory and organised so that you get a better understanding of the subject. Alright, so let's take the memory map in front of you, which is shown on the left hand side of the screen, and go through these sections one by one. At the top we've got high mem. This line here represents high mem. Now this is basically the first address at the top of the memory which is not available for use by BBC Basic. So when we're looking at the top of the stack, really it's one below that value. So the stack will expand when we add things to it, addresses to it. So those kind of addresses will be things like you jump to a procedure, or you jump to a function, or do a go sub or something like that. So when you jump to the place that you're going to go to, the procedure or the function or whatever, it will put the return address on the stack. So this will push this down. I mean, at the beginning that line will actually be up here, so if you haven't used the stack in any way, it will go up here and it will gradually push downwards into this available space here. And that's what this arrow is indicating, that it's going in that direction when it fills up. So this is the extent of the stack. That's how far it's gone from a high mem -1 down into this available space. here we have low mem. So low mem is going to be, unless we change it in some way, is going to be the same as top. And top is the address of the top of your program, the extent of your program or programs. The heap is where we store all the variables basically that you're creating for your program, and will increase in size the more program variables you've got and things like data structures and so forth, and it will push in this direction into the available space. So what happens is, as this expands, as you start declaring more variables, this will expand here. You generally know, unless you're doing it dynamically, what the size of the heap is likely to be. What's more difficult to predict is the stack. So if you go into some sort of recursive algorithm where you call it the same procedure from that procedure itself, then this will start to grow dramatically. And if those procedures are also generating more dynamic structures here, then it's quite easy for this space to become unavailable. And what will happen is, if it becomes unavailable, there's no more room, then you will get a no room error and the program will just stop with that error. So we talked about the stack. You know what the stack is for. It's those return addresses that get pushed up on here. This is for all your memory variables and your data structures and so on. These are sort of dynamic in the way that they move. One of the things that we touched upon in an earlier video was strings. So if we've got, for example, real numbers and integers that we're storing on the heap, then that's fine because we know how many bytes they're going to take. But if you're storing strings, for example, on the heap, those string values might change. The next time you reassign the value to that string, if the new string is larger than the existing string, a new allocation is created on the heap and that variable is pointed to that new allocation, and the existing space on the heap is just left as it is, unused, becomes unusable and wasted. It's just taking up space on the heap. So you need to have some sort of approach to that which will prevent you from doing that. So just have to think carefully about the programming. So if you have something that you know may extend to 256 characters long, then you need to just make sure that you dimension it appropriately to that size, so you can put whatever size string that you like in there and it will never lose the allocation. There are other ways of doing that, but that's not for this video. So hopefully that gives you some information on at least these first three bits there. So if we go down to top, which is over here, which represents the same line really, where your user programs is, and then you've got page at the bottom. So if we just skip past those two and then go to the bottom one, this is about I think it's 1700. 1.7k, something like that, of a basic interpreter workspace. That's just allocated for that, so that will stay where it is, and that's where your programs start. So you can't change top. That's inspectable variable, but you can't change it. But that is an indicator of. It tells you where it ends, basically. Page is where it begins, and I think that starts at 17408, I believe. So that's where that line starts. And then you could actually change the page if you wanted to, if there's a particular reason for it. The size of your program basically is going to be between top and page, so that minus that will tell you how big this is. Understanding where the stack is at any one moment in time, the extent of the heap, is not straightforward. We may or may not cover that in this video, but this is just to give you an idea of how this all hangs together. So what I'm going to do now is I'm going to try and bring up a program that I've got. We'll show you how to break the stack. Okay, so let's see. So I'm going to cd into the vid directory, and then we'll load something called break stack. So I'll actually list this now, and I'll just show you. Be quiet, phone. I'll just show you what we got there. Right, so it's a stack in progress. See what happens with this. Okay, so let's go back to the beginning actually. Forget line 10. What we've got is two static variables there, integers. We've got a % equals 1 and we've got b % equals 15,000. So the next line we call proc sub, which is defined here, and then after that we've got end. What we find here on line 60, it says if a is bigger than b, which it won't be in the beginning because A begins at 1 and that goes up to 15,000. Then we'll end proc. Right, so we'll go back to there and this just halts the program. Otherwise, we'll print A rather, and then we'll increment A% by 1, and then we'll call the same proc sub. We're going back here. So every time we do that, we're going to put the return address, which will be in the second instance that this is called from itself. It will be the proc sub address itself, and this will start pushing down this stack, and it will fill up this space until we get to a point where there's no more space left. So what I'll do first is I'll make B 5, right? So I'll go in and edit 20 just to show you how this runs. So we'll make that just five iterations, and I'll run this. So it just counts up to 5 because we gave it 5 iterations. So now we had no problem there were no errors. And I'll go to 20 again, and I would change that to 15,000. Clear the screen and see what happens now. This is going to take a few moments to run, but you'll see it's counting up there very quickly, so it's not going to take too long, probably about 7 or 8 seconds, something like that. Maybe a bit longer. So we got to 11,864 on the count of A%, and it's given us no room at line 60. So that means whatever was here, right, in the program, it's had to push this all the way down, and it can't find any more space to store on the stack, which will have moved all the way down there to there. Basically, that's what's happened. So in essence, that is how the stack works. When we talk about the heap moving into the space and finding no room, we get a slightly different error message. The error message that we get, we'll see in a minute. So what I've done is to modify the break stack program, and on line 5, which wasn't there before, I've actually tried to dimension C% to first address of a space which is 50,000 bytes long, which is more than we got available to us. So if I did this, which is to run now, we'll get a message telling us there's a problem. It says dim space at line 5, which is basically saying I haven't got enough space. We see a no room error message from the stack when we run without this line. Eventually at line 11,000 or something like that, 11,200 I think, I can't remember. But what I'm going to do now is I'm going to reduce this to 10,000, and we'll see what effect it has when we try and break the stack. So I'll do an edit 5, and we'll just change that to 10,000. So when I run it now, what I'm expecting to happen is it to not actually get as far as it would have done before with the stack. Instead of going to 11,000, I'm expecting it to only manage, I don't know, perhaps 75% of that. So let's just try it and see what it does. I've literally just done this now, so I don't know what the result will be, but let's see. So it's still running. Where will it go? Nobody knows. Right, okay. Is that 75%? But it's about a quarter or something, so yeah, it's around that kind of figure. So we get the no room message when we're trying to allocate something onto the stack. So that, I think, covers the space issue and how you can expect to see errors coming up if you breach the amount of space available. So which brings me on to actually the issue with strings. So there's another possible thing you can do to help you to prevent excess storage on the heap when you're dealing with, well, not just strings, actually any variable, is the length of the variable name. So I mean, in programming we like to try and use variables with names that make sense, but if you're limited with space, then shortening those as much as is sensible may help you if you have a lot of variables, reduce the load on the heap. I mean, back in the day when this BBC Basic was running on a BBC, they were using the shortest variables they could possibly do, and they didn't make any sense really to anybody except the programmer probably. So if you were another person looking at it, you'd be in awe of the confusion usually. And not only that, they would crash the programs, by putting variable names right next to a keyword and stuff like that, which makes it even more unreadable. I hate that. I really cannot abide obfuscated code, by using one character variable names and stuff like that, unless it's done in a very macro sense, so it's in a small area of code. So if you're using local variables, it's easier to read if it's a small subroutine, or function or rock. So it's a bit of a trade-off really, trying to make your program readable and also trying to make it smaller if it's a problem. What I tend to try and do is the procedures and the functions, which is really all I use, a meaningful name, and then try and be sort of just sensible with the other names I use for other variables. Try and trade off like that. Yeah, that can help. But yeah, so let's have a look at how much memory we actually have got available. So 64k. So if I print, because there's nothing in there at the moment, print high mem minus low mem. So 47k available to you in total. That's much more than you ever had on the BBC Model B, because you only had a maximum, well, not even 32k. Okay, so there's one last thing I wanted to do, was to talk to you about page and the first line of code. So page is where your program starts, and that is literally your first line of code. So here we've got on the top 10 says print A, B, C, D, E with two quotes around it. And what I've done is put a single line execution there, and so this is a for loop. So it will go from page, the first line, first address, and it will go to page plus the first character, which is the length there, minus 1. So that will give us all of the data regarding that first line. So we then go and print that. So str $, it actually stringifies, if you like, the value of x. So let's see what we've actually got in there. So the first byte is actually the length of this line of code, 13 bytes long. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. The second 2 bytes, with the least significant byte first, is the line number. And as you see, that's 10. And if you look up there, that's line 10. The more significant byte of these 2 byte line numbers, and don't forget we can go up to 65,000 lines, is 0. Because it's it's just 10, so it's going to be 0 in there. The next byte is the token for the keyword. So that happens to be 241. That relates to the keyword print. And then the rest of this, in this case, just happens to be what we see there in this string. So 32 is space, and then 34 is going to be a quote mark. 65 relates to A. And I purposely put A, B, C, D so you can see this increment in there. A, B, C, D, E. And then we've got another quote. And then finally we've got the 13 or a 0D, which would be the carriage return. And that's what terminates the array of values. So that says this is the end. I just wanted to show you that to sort of top off what we've done in the video. Demonstrates how the variables are actually stored, how you can interrogate them programmatically. Well, I hope you enjoyed the video, found it useful and informative. If you have, please hang a like. And if you haven't subscribed, you know you need to subscribe. And that would be great, because it really helps me out. Anyway, I will see you next time. It's gonna be alright.